today, we're going to dive into a really cool question. How exactly does a drone manage to just hang perfectly still in the air? We're going to break down the key ideas from a book that makes drone control surprisingly easy to understand, starting from the absolute basics.
So the book we're using as our guide is MATLAB Drone Coding for Beginners by Dr. Mohin. And it's awesome because it's made for people who want to get the how and the why without, being buried in super heavy math from page one. It's all about taking a practical, step-by-step approach, building up your knowledge one idea at a time. So yeah, let's just start right there with that big question. How does a drone just hang there? It's seemingly defying gravity, just frozen in place. It looks so simple, but it's actually the first and maybe the most important problem you have to solve to make a drone fly at all.
Well, that stillness, you see, it's not calm at all. It's actually a furious, non-stop battle against the pull of gravity. And if you want to win that battle, it all starts with understanding one single, absolutely crucial principle. And that principle is called hover thrust. Think of it like a perfect balancing act. The propellers are spinning just fast enough to create an upward push. That's the thrust. That is precisely equal to the drone's own weight pulling it down. Not an ounce more, not an ounce less. It's a perfect, delicate equilibrium. Okay, so what happens when we break that perfect balance? Well, take a look at this plot of excess thrust. It's pretty simple. When that blue line goes above the 0 mark, it means our upward force is winning the fight against gravity, and yep, the drone climbs. If it dips below 0, gravity wins and the drone comes down. It's a perfect visual of that constant power struggle. All right, so we get it. We can go up, we can go down. But how do we actually tell the drone what to do? The most basic way is to just give it an order without waiting for any feedback. In the engineering world, they call this open loop control, and it's the next logical step on our learning journey. So the book starts with two really fundamental command types. First, you have a step input. This is like flicking a light switch. Bam! You instantly tell the motors to jump from one speed to another. Then you have a ramp input, which is more like slowly turning a dimmer switch. It's a gradual, smooth increase in motor speed over time. And this right here shows the difference perfectly. On the left, that step input makes the drone's velocity just jump almost instantly. It's really fast, but also pretty aggressive. But on the right, the ramp input gives you that much smoother, more graceful increase in speed. So the big takeaway here is how you give a command can be just as important as the command itself. Now, this is all great for basic movements, but what if our goal is precision? What if we want the drone to fly to exactly 1.5 meters and just stay there, no matter what, even if a gust of wind comes along? Well, just telling it what to do isn't going to cut it. For that, we need to give our drone a brain. This is where we get into closed-loop control. Instead of just blindly following orders, the drone is now in this constant feedback loop. It's always asking itself, where am I right now? Where am I supposed to be? It calculates the difference, the error, and then automatically adjusts its own motors to make that error as close to 0 as possible. It's basically thinking for itself. And the book walks us through building this brain one piece at a time. First, you have P for proportional. This is kind of the brute force part. The bigger the error, the harder it pushes back. The problem is it tends to overshoot and then wobble. So we add D for derivative. This acts like a set of shock absorbers, calming down those wobbles by anticipating where it's going. And finally, we add I for integral. This is like the controller's memory. It looks at small, persistent errors over time and says, hey, we're always just a little bit off. Let's fix that. Put them all together and you get the full PID brain, a system so powerful it's used in everything from your home thermostat to cruise control in your car. Okay, so we've built these different controllers, these different kinds of brains for our drone. But which one is actually the best? Well, to figure that out, the book sets up a fantastic head-to-head comparison. So here's the test. We tell every controller to hold the drone steady at 1.5 meters. Then, right at the 2-second mark, we simulate a big gust of wind pushing it straight down. And just look at the results. The blue and yellow lines, those are the P and PI controllers. They just oscillate like crazy. The PD controller in green is better, but watch that black line. That's our full PID controller. It barely even flinches. It just smoothly and quickly returns right back to its target. It is the clear winner, no question. So the really critical point, just as the book says, is this. Even though every one of these controllers had the exact same goal, their methods, you could almost say their personalities, lead to completely different results. It proves that choosing the right controller isn't just about getting the job done, it's about getting it done well.
And this table just sums it all up perfectly. P control, it's simple but really shaky. PD gives you that smoothness, but it can leave a small error at the end. PI is great at fighting those stubborn errors, but can be a little too aggressive. And PID? Well, that's the one that gives you the best overall balance, taking the best parts of all the others.
And there you have it. That's the entire learning journey in a nutshell. We started with the basic physics of just hovering, moved on to giving simple open-loop commands, and then we actually built a sophisticated closed-loop brain for our drone, and finally tested each version to see which one performed the best. Mastering altitude control is a huge first step, but honestly, it's just the beginning. It's the foundation that all the other, more complex drone behaviors are built on top of. So, what's the next level? Well, from here, the door is wide open. You can expand into full 3D modeling, you can learn to control the drone's orientation, its roll, its pitch, its yaw. You can teach it to follow complex flight paths, or dive into even more advanced modeling techniques. Once you have this foundation, you can go anywhere. Now, what we've done here is really just give you the high-level map of the journey. But if you want to actually take the trip yourself, get your hands on all the code, follow the detailed walkthroughs, and do the practice exercises that really build your skills, then you can find absolutely everything you need to start coding your very own drone controller in MATLAB Drone Coding for Beginners. It really is a fantastic starting point for anyone who's ready to go from theory to actually doing it. Thanks for joining us for this explainer.